Hello, in this video we'll be looking at how you can judge and compare the strengths of Bronsted-Lowry acids and bases, particularly in the context of a Bronsted-Lowry reaction. So in every Bronsted-Lowry reaction you're going to have an acid, a base, a conjugate base, and a conjugate acid. And within that reaction you're going to need to compare the strength of the acid and the conjugate acid and the base and the conjugate base. So you'll be comparing your two acids and comparing your two bases. And there's a list of criteria that you end up having to use most of the time when comparing your species in your reaction, particularly your acids. And we're going to go through this criteria and sort of look at how you can apply it in the different scenarios where the specific criteria apply. So the first thing you want to look at is your overall charge. If your overall charge on your two acids is different, then that's a very easy way to spot check to see which one is stronger. Let's take a look at that. So we are going to compare these two acids to see which one is stronger. We've got HSO3- and we've got HPO4-2-. So first thing you want to draw your attention to is the fact that the overall charge of these two things is different. This one is 2- and this one is just minus, or you could also say just -1. So the general rule is the more positive the charge is on your acid, the stronger that acid is. So you'll see that HSO3 is more positive than this. It's just -1 versus -2. So because this guy right here is more positive, we will say that it is the stronger acid. The same logic applies for the most part to bases. The more negative your base is, typically the stronger your base is. So a more positive acid is stronger, a more negative base is stronger. So they kind of work in opposites that way. That's because we want our bases negative and we want our acids more positive. And it's all relative as well. So what if it isn't just convenient to look at the charge? Say your charges are the same, and I will say, most of the time when you're dealing with these Bronsted-Lowry reactions, the charge will be the same. Sometimes you get lucky and the charges are different and it's pretty easy, but you're not always so lucky. So if the overall charge is the same, we have to look at this concept known as the charge center. And the charge center is simply going to be the element that the acidic hydrogen used to be bonded to. And the acidic hydrogen is simply the hydrogen that pops off when you go through your reaction. And if you look at the conjugate base of your acid, the charge center will be negatively charged. And there's two different scenarios when it comes to the charge center. If your charge center is the same, you're going to look at resonance and inductive forces, depending on the scenario. So first let's talk about resonance and how resonance affects if your charge center is the same. So we want to compare these two acids to see which one is stronger. And ultimately what we're going to have to do is look at the conjugate bases of these acids. So remember, the conjugate base simply means we pop off the acidic hydrogen. So I'm going to go ahead and pop off the acidic hydrogen from both of these and write out the Lewis structures of those conjugate bases. So here I've gone ahead and drawn the Lewis structures for the two conjugate bases here. We've got BrO- and BrO2-. And the thing we're looking for here is resonance, right? And the reason that you look at the conjugate base of the acid is because you kind of have to work backwards, okay, when you have to look at the charge center. And that's because if your conjugate base is weaker, the acid it came from is stronger. So like I said, it's like working backwards. You determine the strength of your conjugate base first, and that allows you to know the strength of the acid that that conjugate base came from. And resonance is considered a weakening force, and that's because resonance stabilizes a molecule, right? Because resonance simply means that electrons are highly mobile, and the more mobile your electrons are, the more stable your molecule is, because that charge is constantly moving around. So let's look at these two Lewis structures to determine what's going on with the resonance. So for BrO minus, this molecule here, this can't even do resonance. There is no resonance structure for this molecule, right? This is the only way you can draw this Lewis structure validly. Versus BrO2 minus, this Lewis structure can have a resonance structure, and that's because that double bond can be on either one of these oxygens. You know, your double bond could be on this oxygen, or the double bond could be on this oxygen. It doesn't really matter. Therefore, this structure here can do resonance. And because this structure can do resonance, it is a weaker base. And because this base is weaker, that means the acid that it came from is stronger. So if you have more resonance in your conjugate base, that makes your original acid stronger. Therefore, HbRO2 is stronger than HbRO because of resonance. So just to sort of solidify that point that resonance makes your acid stronger, this here is an order of increasing strength, right? And that's because each molecule has more resonance, right? HbRO has no resonance in the conjugate base. HbRO2 has some resonance in the conjugate base, and HbRO3 has more resonance in the conjugate base, right? So kind of a dirty little trick that you could use. The more oxygens you have, typically, in this context at least, you're getting stronger in your acid. Although I wouldn't take that as a general rule. It just kind of works in these particular oxyacids. But you always want to look at the conjugate base in your resonance structure, if your conjugate base can have resonance structures, as your main line for the strength, if your molecules can do resonance. So now let's look at the other force that comes into play when you have charge centers that are the same, and that's going to be inductive effects. What is induction? Well, induction is simply the impact that a highly electronegative atom has on your molecule. So if your molecule has a highly electronegative atom in it, that highly electronegative atom is going to pull electrons towards itself. And when it does that, it stabilizes the conjugate base. And remember, the more stable your conjugate base is, the weaker it is. The weaker your conjugate base, the stronger the acid it came from is. So inductive forces are much like resonance forces. They are stabilizing, and they weaken the conjugate base, which makes the acid it came from stronger. And for inductive forces, you really want to think of Funkelbryce, because those are your most electronegative elements. And if you see one of those Funkelbryce elements in your molecule, you're going to want to think of the inductive effects it's having. So let's look at an example of what that would look like. So let's look at these two conjugate bases. Now, originally they would have had a hydrogen coming off of this oxygen on both of them, but I went ahead and simplified things and went ahead and drew the conjugate bases. So they're nearly identical. The only real difference is the fact that this conjugate base has 3 hydrogens on this first carbon, whereas this guy over here has 3 fluorines on that first carbon. Remember Funkelbryce, fluorine is highly electronegative. So what that means is the fluorine is drawing the charge from this oxygen towards itself. And what that means is that it's stabilizing the charge in this molecule, which means this molecule is more stable than this one. because this molecule is more stable, the acid it came from is stronger. So this conjugate base came from the stronger acid compared to this one because of those inductive forces. So this came from the stronger acid of the two. So let's take our conversation about inductive forces that one step further. So what happens if both of your conjugate bases have inductive forces? Well, in certain cases it comes down to electronegativity. The more electronegative your element is, the stronger the inductive forces are, right? So that's one way to look at it. Another way to look at it is proximity to the charge center. If you look at these two, this one has the F on the first carbon, this one has the F on the second carbon. Because this one has the F closer to the charge center, this guy would come from the stronger acid. Because the closer your electronegative element is to the charge center, the stronger the inductive forces are. The further away that electronegative element is, the weaker the inductive forces are. So inductive forces increase with the more electronegative your element is, and they increase with proximity to the charge center. So the closer you are to the charge center, the stronger the forces are, which gives you a stronger acid ultimately, versus being further away would give you a weaker acid. And just to quickly illustrate what I was saying about the more electronegative element wins, in this case we've got an F and we've got a Br. Now if you know Funkelbreich, you'll know that fluorine is much more electronegative than bromine. And because fluorine is more electronegative than bromine, it wins. And this would come from the stronger acid because the inductive forces are stronger for fluorine than they are for bromine. So that's all well and good for comparison if your charge center is the same. In that case, we looked at examples where they were the same. And that's when you want to bring in resonance and induction. Resonance and induction don't necessarily have more importance, one or the other. It really just depends on the situation. If your molecule has resonance, then resonance is going to matter. If your molecule has inductive forces, then the inductive forces are going to matter. Neither one is more important than the other. But let's say you have different charge centers in your acids. And that's when you're going to have to look at size and electronegativity, and they're going to work in two different scenarios. So here is a nice classic example of having two different charge centers. And our acids here are HF and HBr. So you might be thinking to yourself, well, I know the HBr is one of my strong acids, and I know the HF isn't one of my strong acids, so I can know just by memorization that HBr is the stronger acid. There's no need to even worry about this one. I can just look at it automatically and tell which one is stronger. And that's the case in here, but it's not the case all the time, and you will get many examples where you don't have just one of the strong acids sitting there waiting for you to look at it. But let's actually apply some of our logic here, some of our strength criteria logic, to actually make sense of why HBr is stronger than HF ultimately. And for that, we're also going to need to look at the conjugate bases here. So our conjugate base for HF is F-, and our conjugate base for HBr is Br-. And here you can see clearly that the charge centers are different. So what exactly is the relationship between fluorine and bromine on the periodic table? They're in the same column. So as my crude illustration here shows you, fluorine and bromine are in the same column of the periodic table. They're in group 7A. Fluorine is up high, whereas bromine is down low. And if you know your periodic trends well enough, you'll know that as you go down the periodic table, what increases? Size. So size increases as you go down a column. Well, as you increase in size, for your charge center, if you're in the same column, your acid is going to be stronger. So the general rule of thumb here, looking at your charge centers, if your charge centers happen to be in the same column of the periodic table, then size is what matters. And the bigger the size, the stronger the acid is. And that's only going to apply, though, if they're in the same group. So F and Br happen to be in the same group. Br is bigger, therefore HBr is the stronger acid. And if you wanted to know the reasoning behind that, the bigger your element is, the more shells it has, the easier it is to pull the hydrogen off. Remember, it's all about getting that acidic hydrogen to pop off. The easier the acidic hydrogen pops off, that's going to affect how strong your acid is. Because the stronger your acid is, the easier it is for that hydrogen to pop off. Fluorine is really small, therefore it pulls really hard on that hydrogen that it's bonded to. Bromine is much bigger, therefore it has less of a pull on that hydrogen, making the hydrogen easier to pop off. So let's look at the other situation where we see this happen. So let's take these two acids. We have H2S and we have HCl. Now I know you could also look at HCl this time also and say, hey, HCl is one of my 6 strong acids. I know it's going to be stronger than H2S. Well, let's again apply our logic to this situation. So what's the relationship between S and Cl on the periodic table? Well, they're right next to each other on the periodic table, right? They're in the same row. And if you're in the same row, electronegativity is what's going to be important, right? So which one is more electronegative, sulfur or chlorine? If you remember Funkelbryce, you'll know that chlorine is more electronegative than sulfur. And because chlorine is more electronegative, that means HCl is our stronger acid. So to recap that, if your charge centers happen to be in the same column, size is what matters. The bigger the element, the stronger the acid it came from. If you're in the same row of the periodic table, electronegativity is what's important. And the more electronegative your element, the stronger the acid it came from. So that's the two different scenarios where you look at if your charge center is different, how do I compare them? And that's how you compare them, based on if they're in the same group or in the same row. So why does all this stuff even matter? Why do we need to compare the strength of the acids and the bases in these Bronsted-Lowry reactions in the first place? Well, it matters when it comes to your actual reaction. This is the desired scenario for your Bronsted-Lowry reaction, because this scenario means the reaction moves forward. You need to have the stronger acid and the stronger base on the same side of the equation. And ultimately you want your weak base and your weak acid as the products of your reaction. If it was kind of jumbled up, let's say you had a strong acid and a weak base, then your reaction isn't going to move forward. So that's why you need to compare, because in every Bronsted-Lowry reaction you have 2 acids and 2 bases to compare. And ultimately, if your stronger acid and your stronger base are on the same side, that means the reaction can actually move forward. But you need to be able to judge the strength of those two and compare them in order to know which one's stronger and which one is weaker. And hopefully this helps to analyze the strength of these Bronsted-Lowry acids and bases and compare them for your reaction.